Hi everyone and welcome to the learning curve. In this video I will be providing a worked detailed solutions for a typical introductory statistics final exam paper at universities. Here we are told to show all your workings to receive full credit. Only write one answer for each question. If there are more than one answers, you will receive 0 points as the grader does not choose the correct answer even if one exists. So it's important to have one solid answer provided for each question. In the first question here we are told that the time that it takes a driver to react to the brake lights on a decelerating vehicle are critical in helping to avoid rear-end collisions. Research suggests that the reaction time for all in-traffic response to a brake signal is normally distributed, having a mean value of 1.25 seconds and a standard deviation of 0.46 seconds. We are asked, what is the probability that the reaction time will be between 1 second and 1.75 seconds? So we are asked to write down the probability statement to calculate the probability of interest and ensure that we use the correct notation here for 3 marks. Let's address this question. So because we're asked to find the probability that the reaction time is between 1 second and 1.5 second, then the probability statement would simply be the probability that x is greater than 1.00 but less than 1.75, both in seconds. That's all really. That's the probability statement. So this is read as the probability that x is greater than 1 but less than 1.75. And this is generally how you would write the probability P that a value falls in between two numbers. The two numbers here are 1 second the lower limit and 1.75 seconds the upper limit. So we compute the probability that x is greater than 1 but less than 1.75. That's what we're interested in calculating, and so that is the probability statement that satisfies number 1. This is a normal distribution problem. We're told that the times here, the reaction times, are normally distributed. So this is a normal distribution problem, and the population mean is 1.25 and the population standard deviation is 0.6 seconds from research that was done. Secondly, we are asked to calculate the z-scores needed to calculate the probability of interest. Write the formula used to calculate the z-scores, substitute in the necessary values, and write the final answer to 2 decimal places for 4 marks. For normal probability distribution, we use this formula to standardize. We use the formula z equal x, which is the value for which you want to calculate the probability, minus mu, the population mean, divided by sigma, which is the population standard deviation. That's a formula that we use to calculate probability for normal distributions. Normal distributions refer to data sets that if we were to sketch a histogram or a frequency polygon, which is a line graph to represent the data, then it would follow a bell shape or symmetric shape. Now, we're next asked to calculate the z-scores needed. So we're asked to calculate the z-scores needed to calculate the probability of interest. So here we're going to have the probability. I'm going to write back this statement here. The probability that x is greater than 1 but less than 1.75 is going to be equal to, so I'm going to standardize these values using the z formula that I just indicated. So this will be the probability, and I'm going to write the formula here as requested. X minus mu divided by sigma, the standard deviation, less than, instead of writing x, I will write z in the middle. And then I'll write the formula in place of both numbers in the representation here. So x minus mu all upon sigma. So we're going to apply this formula to both values in the interval. So this will be equal to the probability. X is the value for which we are calculating the probability, which is 1 in the lower limit, minus mu, which is the population mean of 1.25. The population mean is 1.25, divided by the standard deviation, which is also given to us, that's 0.46. This is less than z, which is less than, and then we're going to apply the formula x minus mu all upon sigma for the higher value in the limit, which is 1.75. So we're going to have there 1.75 minus the same mu value of 1.25. And of course, this is being divided by sigma, where sigma represents our standard deviation, and that is in particular the standard deviation of the population of interest. That is the population specified in the question. So this is over 0.46. So we're going to now simplify these to satisfy what the question is asking, which is to write the formula used to calculate the z-score, substitute in the necessary values, which we have. And then we're going to calculate the z-scores here. So this will be the probability. And then we're going to simplify this. So when I take 1 minus 1.25 and then divide all of that by 0.46, we get 0.54, which is less than z, which is less than, on the other side, when I take 1.75 minus 1.25 and then divide by 0.46, we will get 1.09. So those are the z-scores. That's what we call those, the z-scores. Now we're asked in the next question to calculate the probability of interest. And what we're going to do here is that we're going to draw a standard. We can draw a standard normal table at this stage, standard normal curve. And the standard normal curve would basically show our area of interest. We have 1.09, which is our upper limit, on the right of 0, because the center of the standard normal curve has a value of 0. So we're drawing the standard normal curve to represent the area of interest. And on the left of 0, we'll have negative values. So the negative 0.54 is going to be to the left of 0. So the area that we're interested in here is the area between negative 0.54 and 1.09. That is the area of interest to the researcher. And to find this area of interest, what we're going to do is that we're going to take the table reading for the higher value. So we're going to take the table reading Z, the Z table reading for 0.54, negative 0.54. And we're also going to take the Z table reading for 1.09. Let's see what they are. So to get this, what we will do is that we will go to the standard normal table, and we're looking for negative 0.54 firstly. So we go to negative 0.5, and then across under the column that says 0.04. So firstly we go to negative 0.5, and then across under under 0.04. So let's match those values. 0.04 is the fifth column there. So from negative 0.5 here, we would go across 3, 4, 5. This is fifth column. So the answer is 0.2946. 0.2946. That 0.2946 is the probability associated with the lower limit here, 0.2946. When you have these kinds of intervals on the normal curve, on the standard normal curve, what you do is to take the standard normal table reading for the higher value, which gives you the probability associated with the area to the left of that value, and then also take the probability of the associated with the lower value, and subtract them. Probability has to be positive, so we would subtract the probability associated with the lower value from the probability associated with the higher value. So again, when you have an interval like this, for which you want the probability of the area between them, take the standard normal table reading for the higher value, which would be 1.09, and also take the table reading for the lower value, which in this case is negative 0.54, and just subtract the probability associated with the lower area, the lower value rather, from the probability associated with the higher value. So we're going to go down here to 1.09, search for 1.09 on this table, positive 1.09 that is. So there we go, we're going to go to 1.0 and then go straight across on the 0.09, and that's 0.8621, 0.8621. So we have now found that the probability associated with 1.09 is 0.8621. So therefore, I'm going to conclude here that the probability of of z greater than negative 0.54, which is the statement here, the probability that z is greater than negative 0.54 but less than 1.09 is equal to the probability associated with the larger number, which is 1.09, and that probability would be 0.8621. Take away the probability associated with the lower of the two numbers, which is the probability for negative 0.54, which is 0.2946. And then we simply subtract them, and we get a result of 0.5675, which means that there's a 56.75% chance, so a 56.75% chance that the interval for this data set, which is the reaction time, will be between 1 second and 1.75 seconds. The probability of that happening is 56.75% for this normally distributed population. In the next question here, we are given a graph. This is the graph. Just constructing it here quickly. This is the graph that we're given. And we are given the area here with the middle of the standard normal curve being 0. And very, very easy, we're asked to identify the boxes that are numbered, identify the number that should be at the particular box. And I guess from the graph I drew earlier, it will be very easy for you to pick up what the answers are here, which I would have also explained. So there we go. This is 3 right here. Nothing was given right there, but we always know that the middle of the standard normal curve, the z value in the middle of the standard normal curve is always 1. So we have 1, 2, 3, and here we have 4, and we're asked to state all of these boxes. Clearly, based on the graph I drew here, the upper value is going to be the value to the right of 0. 0 is the value that we'll fill in the center here. 1.09 is going to be on this side. Negative 0.54 is the value on this side, which corresponds to right here. 0 is right here, and 1.09 is right here to the right of 0. And the probability that we worked out, 0.5675, is the probability of the entire area between negative 0.54 and 1.09. So we'll put 0.5675 here. Awesome. And that is how this is done. So that takes care of the first question on normal probability distribution. Our next question here says, CNN Money reports that the mean cost of a speeding ticket in the year 2002, including court fees, was $150. A local police department claims that this amount has increased. to test their claim, they collect a sample from data from a random sample of 160 drivers who have been fined for speeding in the last year and obtained an average, which is the sample mean here, of $154 per ticket. Assuming that the population standard deviation is 17.54, is there sufficient evidence to support the police department's claim at the 1% level of significance? So what we're asked to do here is to carry out a hypothesis testing for means. All right, so we're carrying out a hypothesis test for means. In other words, we're asked to test the claim by the police department that the mean cost of a speeding ticket has increased from what obtained in the status quo. So we're challenging the status quo, which is that the mean cost of a speeding ticket, including court fees, is $150. That is the established value, the established cost that we are challenging based on the hypothesis generated by the police department, which claims that this value has increased from their observations. In order to test their observations, what they did was to collect data from a random sample of 160 drivers, which revealed a sample mean of 154. Assuming that the population standard deviation, which is also given to us, 7.54, is there sufficient evidence to support the police department's claim? So we're going to test this hypothesis to see if the mean has increased based on the claim made by the police. We can use the Z distribution or standard normal distribution to carry out this test simply because we know the population standard deviation, and moreover the sample size is considered to be large, which is greater than or equal to 30. The sample size is 160. And the standard deviation of the population is known. So the conditions for using a Z test or standard normal distribution principles to carry out this test is valid. So we're asked, firstly, to write down the null and alternate hypothesis to conduct this test. Use correct notation, and this would be 4 marks. So firstly, we're going to write the null hypothesis. The null hypothesis is HO. Then I write a colon, mu equal the mean that is being challenged. The null hypothesis is always the default mean that is being challenged for tests of means, and or the old data or the old and established data that is being challenged. And in this case, the old and established data that is being challenged is that court fees were $150. So we say mu equal 150 for the null hypothesis, which is the mean that is being challenged. Then we get to the alternative hypothesis, H1 or HA, which we are asked to state as well. And since the challenge that is being put to this old condition that mu is equal to mu, which is mean, for the population is equal to 150. Since the challenge that is being put to this is that the amount has increased, then it will be a one-tail test, specifically a right-tail test. So the alternate hypothesis will be mu greater than 150. Remember that the value in both the null and alternate hypotheses will be the same, right? One represents the original condition being challenged, which will have an equal to involved in it, and the other is a challenge or contradiction to that null hypothesis depending on the specific circumstances of the situation or question. In this case, what is being put forward by the local police is that the mean amount has increased, so the alternate hypothesis would be that the mean has increased beyond 150. The next thing we're asked to do in part B of this question is that we're asked to calculate the test statistic. State the letter used to represent the test statistic. Write the equation for calculating the test statistic, and then substitute the necessary values. We're going to write our answer to 2 decimal places, all here for 4 marks. So here Z is equal to X. This is the test statistic. Z is equal to X bar minus mu divided by sigma, here, sigma upon the square root of n. And this is the test statistic for hypothesis tests for single means. Now we're going to fill in the relevant numbers. X bar, which is the sample mean, as we indicated before, is 154. So we're going to insert 154 there. Mu will come from the null and alternate hypothesis. The value in the null and alternate hypothesis is the mu, which is 150. Sigma is the population standard deviation, which is given to us in the question as 17.54, yes? So that's 17.54. And we're dividing by the number of observations or sample size, which is 160 drivers who were sampled. So we're dividing here by the square root of 160. The numerator is going to give us 4, 150. Take away 154, take away 150. And on your calculators, when you take 17.54 divided by root 60, you're going to get 1.3866,587. So as many decimal places as possible for this is good. And so we end up getting an answer of 2.88. That's my test statistic value or calculated value. Good. So we've taken care of A, B, and now C, which says we should write a probability statement of the p-value in terms of the test statistic. And first write the general formula and then substitute the value as necessary. Now, because this is a one-tail test, in fact it's a right-tail test, then the general formula would be the probability that Z, large Z, is greater than small z. Or you could have said the probability that z is greater than a. This is really just symbolic, this small z. You could say probability that z is greater than a or greater than b, any letter is fine. But here, the most common generalization is to say probability that large z greater than small z. Greater than small z, we're using a greater than here between the large z and the small z in this generalization, only because it's a one-tail test, particularly a right-tail test, because the inequality in the alternate hypothesis is a greater than sign. If it was a less than sign, then you would use large z less than small z, and if it was a not equal to, where in situations where we have a two-tail test, then it would be z, large z, not equal to small z. That's what it would be. Okay, so this would be equal to the probability that large z is greater than, and we're just going to substitute the value for small z that we're going to substitute here is the calculated value or test statistic value, which is 2.88. And that satisfies this question. Right? That's the probability statement for the p-value. The p-value is the probability value that is associated with this test statistic. All right, that takes care of that. Now in part D, it says if the below curve corresponds to the density curve of the test statistic, indicate the value at the center, 1, indicate the location of the test statistic, 2, and 3, shade and label the corresponding area to the p-value. Okay, so this is the curve that was actually given in the question. I'm just going to draw it here. Okay, that's the curve that we were given, and we were given a shaded area. Naturally, the shaded area that would be given is to the right, and the reason for that is because this is a right-tail test dictated by the fact that the alternate hypothesis has a greater than sign. If it was a left-tail test, we would have shaded the left tail, in which case the alternate hypothesis would have a less than sign. Or we would shade both tails, left and right tail, if the alternate hypothesis had a not equal to, which we call those tests, two-tail tests. Okay, so all we're asked to do here is to label this diagram. So we're going to locate the center. The center is, says indicate the value at the center. The value at the center of the standard normal curve is always 0. All right, and we're asked to indicate the location of the test statistic and shade and label the p-value. So this is the location of the test statistic, 2.88. It's 2.88 here, which is located right here beyond the p-value. Okay, and that takes care of that. We've filled in the center value. The right tail, if we were not given the right tail shaded, of course we would have to go ahead and shade the right tail. We'll shade an arbitrary area in the right tail. It really doesn't matter. Fundamentally, it's a sketch. So you could have started here, you could have started there. Just make sure that wherever the rejection region starts, this is called the rejection region, just make sure that wherever the rejection region starts is at the test statistic value. So this is the starting point for the rejection region for the hypothesis test. That is the area from the test statistic value and to the right. To the right again because it's a right tail test as dictated by the alternative hypothesis. So this is the rejection region. So that satisfies question D. And in question E, we're asked to calculate the p-value. And this is really simple. The p-value here would be the probability that Z, coming from here, coming from the statement that we wrote here, we're going to calculate the probability that Z is greater than 2.88. And to calculate the probability that Z is greater than 2.88, when you're taking the probability that Z is greater than a value, using the principles of the standard normal distribution, it's always going to be 1 minus the table reading for that value. If it was less than, you just take the table reading for that value, meaning the reading from the standard normal distribution table, and that would be the answer. But because this is a right tail test and we're taking the probability that Z is greater than a value, we would take 1 minus the reading for that value, always and everywhere. And the 1 here is based on the fact that the total probability under the standard normal curve is 1. Why we are subtracting from 1 is that when you read from the standard normal table, the readings that you get are always the probability of the area to the left of a value. So if you need the area to the right, you would have to subtract that probability from the total probability of 1. Okay, so we're going to go to the standard normal table now and we're going to look for positive 2.88. So here we go, 2.8, and then we go right across under 0.08. There it is, we're under 0.08. So the answer here for 2.98, the probability reading is 0.9980. So we go back up and we insert 1 minus 0.9980, which is equal to 0.002, and that's our p-value. This is our p-value, or probability value for the test. This is our p-value, or in other words, our probability value for the test. Okay, so p-value or probability value for the test, so let's just insert it right here correctly. So p-value or probability value for the test, we're actually asked to insert it right here. So it's 1 minus 0.9980, which gives us 0.002, or in other words, 0.2%. 2 decimal places to the right to get this into percentage, so the point would come in front of the 2. So that's the p-value of the test, guys. The p-value or probability value of the test. Now write a conclusion for this hypothesis test in terms of the problem, using the level of significance given in the problem, and state whether the conclusion applies to the population or sample. Well, these kinds of hypothesis tests always apply to the population. You're using results from the sample. From a sampling process carried out, you're using the results from a sampling process carried out to see if there's enough evidence from that sample to reject the old condition, the established condition, as reflected or expressed in the null hypothesis. Okay, so what we're going to do here is that we're going to recall what the level of significance of the test is. The given level of significance here is 1%. That is called alpha. Alpha, the level of significance is 1%. So I'm going to say here, I'm going to write down alpha, the level of significance is 0.01 or 1% as given to us in the problem. And the p-value, which we found, is the p-value is equal to 0.002, or of course 0.2%. Now, here's the rule when you're drawing a conclusion concerning a hypothesis test. Of course, the conclusion of a hypothesis test will either lead to you not rejecting the null hypothesis or you rejecting the null hypothesis. Once the p-value is less than the value of alpha, we reject the null hypothesis. So in this case, p is less than alpha, right? That is, p is less than alpha, that is 0.002 is less than 0.01. And you see, once p is less than alpha, we reject the null hypothesis. So what we're going to conclude here, because p is less than alpha, we reject the null hypothesis and support the alternative. Since we're rejecting the null, null and supporting the alternative, then the alternative says that the mean cost of speeding tickets have increased, which is what the alternative hypothesis specifies here, that the mean is now greater than the old value. So we reject the null hypothesis on the basis that the p-value is less than alpha, and having done that, we support the alternate hypothesis that the mean value of speeding tickets, have increased. Mean value of speeding tickets have increased. Awesome. And of course, as I said before, the conclusion relates to the population, because what a hypothesis test does is that it takes a sample from a population and see if there's enough evidence to reject the null hypothesis. In this case, there is enough evidence based on the fact that the p-value is less than alpha. If the p-value is greater than alpha, our conclusion would be that we fail to reject or do not reject the null hypothesis. So the proposal made by the police department in such a case would not be feasible or supported, more accurately. All right, and this was an example of a typical structured section of an introductory statistics past paper examination at the university level. All right, thank you very much for your time. I will be doing more of these papers, and stay tuned to the learning curve for much more to come. Remember to like, share, and subscribe. Thank you. See you soon.